let's talk about how those enthalpy changes. So every time we have to go through and calculate them, but it would be nice if we had a table that we could just look in and find most of those values. Another thing we're going to talk about today are known as heats of formation. How those come about. So if we're considering just a substance, we can look up its heat of formation and we can utilize that to try and predict how much heat is going to be generated or lost when conducting a reaction. The other thing we're going to try and talk about is these deltas. I said we can only talk about changes in these state functions. We can't talk explicitly about H itself. The reason for that, we'll kind of talk about it today too. So delta HF naught is known as the standard enthalpy of formation. Sometimes it's used synonymously with heat, but when we say that, what are experimental conditions to make the enthalpy and heat exchange the same? Yeah, constant pressure. So sometimes it's used synonymously. It really shouldn't be, because you would have to say, oh, it's the heat of formation at constant pressure, or so on. So when you hear that a lot of times, just know most people leave off that qualifier. They're just not being explicit enough. That's why in Gen Chem, a lot of times when students come in, they call delta H the heat of a reaction. It's only technically the heat of the reaction at constant pressure. So I know it seems very nitpicky, but thermodynamics is all about being nitpicky, as you guys are finding out. Okay. What this is it's the heat of formation for a compound from its constituent elements in the reference. Spelling. Okay. We're going to translate these words into formulas and other things so they're more meaningful. Before we do that though, what do I mean by a reference state for the constituent elements? Anybody remember from Gen Chem? It's a long time ago. A lot of stuff's happened in between then. Got rid of masks, which was cool. Anybody know what a reference state is? What it is it's just how you find the element in its most stable form. So at ambient temperature and pressure. So element in its most stable form. Okay, so as an example, let's consider let's pick a compound. What's someone's favorite compound? Oxygen. I don't want oxygen. I want one other than oxygen. Oxygen does let us live, so that's a pretty good one. I don't want that one. That one's too easy. I want something a little tougher. Zinc? No, I want a compound, not an element. Let me rephrase that. Not an element, compound. Sodium chloride. Okay. Yeah, we can do sodium chloride. Okay, we can look that value up. I don't actually know what it is off the top of my head, but when we're talking about this, we're talking about a specific reaction to form what? Sodium chloride. Okay. What's sodium chloride made up of? It's not a trick question, I promise. Get sodium, okay. And what else?
Chlorine.
Yep, chlorine. How do you find, if you were to take elemental sodium, how would you find it at standard conditions?
Solid,
It's
isn't
a
it?
solid, yeah. You can't ever actually find that naturally, you have to make it. But you can get it. What about chlorine? It's a gas, okay? And I heard, what'd you say, Serena?
CO2.
Yup. Okay, what do I gotta do with the coefficients to make sure that this is true? We have to balance, when you're considering heats of formation, you're saying for every 1 mole of this guy. So we're gonna put a 1 here. What number goes here? 1, so what's gotta go here then? 1/2. Which, I don't know, to me it always feels icky because you're like told constantly, you can't have fractions in there. And now I'm here to tell you, you can have fractions in there, okay? So when we're saying heat of formation, we're talking about taking it, we're talking about forming the compound or changing its physical state based upon its constituent elements. Does that make sense? Okay. Let's talk a little bit more about this. So, delta HF naught, that depends on temperature. It takes place at a specific temperature. And most of the time, they'll say it within brackets. So like, for example, delta HF naught of NaCl solid at 298 K. That's a lot of information in there. A lot of times, they'll just drop the 298 K and assume, okay, you're talking about that temperature. What does that little naught symbol mean, though? This guy. Actually, just SP, a standard pressure. What's that pressure, do you guess? Yeah. Okay. Oh, I lied. It's technically 1 bar, which is close enough to 1 ATM. I'm sure somebody will get mad at me for saying that, but whatever, I don't care. Close enough. Okay. The cool thing about delta HFs, you can find them in a reference table. So the back of your book has a ton of them. Other books have a ton. Those huge CRC handbooks that I made you guys dig through for information, there's a bunch in there too, so you can look those things up. Okay, what's the downside to this though? Yeah,
The temperature in reference to one is temperature experiment.
yeah, so. The temperature may differ. So when you look, we're gonna talk about this later on, probably next week. How do we look at it for another temperature? Not just at that 298 that most tables have. How do we go beyond that? There we'll have to talk about something called heat capacity. Later probably. Another big thing to keep in mind. Delta HF, not for element and its reference state. example, we'll use Ellen's favorite. What's the heat of formation for O2? Yep, 0. Okay. Do we want to see another example where we determine the heat of formation reaction for another compound, or do you feel okay? Shannon says one. Okay, let's figure out question. What is delta HF naught for benzene? Okay, so we're talking about benzene. Does anybody know how benzene's found at ambient temperature and pressure? Or anybody know the formula? Yeah?
Solid.
Nope, not a solid.
Liquid?
It's a liquid. We talk about benzene a lot, but it's kind of funny because we never actually really work with benzene. I've worked with benzene once in my life. Does anybody, why don't we use benzene frequently? Yeah, it's really carcinogenic. It disrupts pi-pi stacking and causes a lot of problems from DNA. So if you can ever get to your DNA. Anybody have any mechanics in the family or older mechanics? Lily, you do? Did they ever talk about washing their hands in benzene?
I don't know, I don't think so.
Yeah, all the old mechanics I know love benzene because it's the best degreaser. You just pop your hands in, bam, comes out clean, nothing to worry about. Most of them are also chain smokers too, so I think they have other things to worry about. Okay, we want to look at delta HF for this system. We can look up the tabular value. And when you do that, it's positive 49.0 kilojoules per mole. Okay, but what reaction are we really talking about when we consider that number? So we got to look at the constituent elements. What do we got?
Carbon.
Yep, and what else? Yep. Okay, how's carbon found at ambient temperature and pressure?
Graphite.
Yeah, it's found as graphite. So we put solid graphite. You need to be careful because there are many allotropes of carbon. Does anybody know any other of the allotropes? Diamond, yep, big one. Other ones, if you've seen Dr. Ogawa's office, he has them in the corner over there. There's graphene, which is a single sheet of graphite. There's buckyballs, which look like a soccer ball. And there's a couple others that they're starting to find, which is pretty neat. Okay, what about hydrogen? How's that found? Yeah. Yep. Okay, what numbers do we need here to balance this out? For a carbon? Yep, for no hydrogen. Yep. So that's the reaction we're talking about. If we let this reaction happen, delta HF, endo or exothermic? Endo. It's going to take energy to make this happen. This is a lot of energy to make it happen. Is this likely to happen on its own? So how do we get benzene? Do we go through this process? Usually not. Usually we refine it from petroleum, that's where we get most of it, and it's a waste product now. But even if we were considering sodium chloride, do we make it this way? Not really. We'll talk about another way we can go about trying to calculate these delta heats of formation. But I want to talk a little bit more about the mathematical form associated with these. So let's talk about standard enthalpy reactions. Delta H of a reaction. When you see a delta, what do you think?
Final minus initial.
I'm sorry, what was that?
Final minus
Finus
initial.
minus initial, yep. When we consider a chemical reaction, what's our final state? Products, yep, products minus reactants. So it's final minus initial, products minus reactants, maybe some crazy calculus going on here. So, we got delta H final minus delta initial. But in this case, delta H naught of products minus delta H naught reactants. If we wanted to make a summation associated with this, we have a summation sign where we sum over all products. We take the stoichiometric coefficient associated with those products and multiply them by the heat of formation of the products. And then we would just subtract off the same thing for reactants. I think I give them the symbol M. And what are N and I? They're N sub I and M sub I again. Yep, they're the moles, they're the stoichiometric coefficients. Did I write something that you can't tell what I wrote?
Yeah, what's that, so HF comma?
Oh, that shouldn't be a comma, I'm sorry, that should be a multiply.
No, the one in the beginning, there.
That's meant to be an I,
Okay.
sorry. It's bad when your 3-year-old starts to write better than you. Events are past. Feels good when it's your kid. Or student. Okay, let's look at another reaction. Calculate delta H naught reaction for. We're going to look at the combustion of methane. We're talking about a combustion. What are our reactants besides methane? Yep. It reacts. What's going to come out the other side for a combustion? Yep. Oh, we want that as a liquid. Okay, what's wrong with this? Not balanced. What coefficient do you suggest for here? 1. That's 1. What's here? Okay, let's balance our oxygens. Actually, let's do hydrogens. What number goes here? In here? Yep, we're good to go. Okay, we want to try and predict what's going to be the heat of this reaction before we even conduct it. Okay, It's always what minus what? Yep. Okay, tell me a product. Yep. Carbon dioxide. And if you notice, I'm writing physical states. The physical states matter a lot. If you look in the back of the book, the value changes based upon the physical state. Okay? What number do I need to multiply this guy by? Yep. Plus, what comes next?
2 times the delta H formation for water.
Yep. Minus, what are we gonna subtract off?
1 times the H.
Minus, what else?
2 times.
All right, awesome. We have an expression for this heat of reaction, but we want to get a value for it. What would you do now? Yeah. Look up these heats of formation. The only two you might be able to find, some books don't even list, what is it? No, that one's good. What did I do wrong here? Oh no, that's oxygen. Sorry, I just sloppy writing. You won't find one for that one. Why not?
Is it 0?
Yeah, it's 0. But you can look up the others. The values I find. 3.51 kilojoules per mole plus 2 times negative 285.83 kilojoules per mole minus 2 times, we want H2O now. Oh no, we want methane, I'm sorry. 1 times methane. Negative 74.8 kilojoules per mole. And Tessa, what did you say about oxygen?
0.
Yeah. Which is nice. When you sum all that junk up, you get negative 8 times 0.4 kilojoules. Okay, everybody feel comfortable with like the mathematical manipulation coming up with that expression and getting this number? Let's talk about what does this number mean. It's on a per mole basis for everything in this expression. So if I have 1 mole of, let's say, carbon dioxide, what's delta H of the reaction?
What we just got in.
Yeah, what we just calculated. Negative 890.4 kilojoules. Sometimes leave it per mole, or we'll just write kilojoules in some cases. What about if I only have 1 mole of water? What's that going to be?
445.
Yeah, that number divided by 2. Lily can do way faster mental math than I can. What was, let's see, negative 445.2 kilojoules. Did I do it right? Everybody feel like they understand what that number means? Okay, any questions about that one? All right, let's talk about Hess's law. So as we were discussing when we looked at some of those other reactions, like when we were talking about the formation of benzene and sodium chloride, we usually don't start with the constituent elements and conduct that reaction and see what delta H is. In fact, for you two who did the bomb calorimetry experiment, you had to find the heat of formation, right? How did you find that heat of formation? You wanted to find naphthalene, right? I didn't have you take graphite and hydrogen and react them with one another, right? What did you do for your chemical reaction?
We did the combustion reaction.
Yeah, you did a combustion reaction. Then you utilized something called Hess's law to work backwards to get to that heat of formation. We're gonna talk about what Hess's law is, kind of as a reminder, and then showing how we can utilize that, okay? Am I right to erase this? Okay, Hess's law. That seems wrong. Do I have an apostrophe S after his name? Yeah,
I think so.
I think so too. Does anybody remember what Hess's law said or stated?
I remember it was like adding the reactions and like flipping the signs and like.
Yeah,
Yeah, and then
you-
you can find the change in entropy.
yeah, and do you remember in Gen Chem what reaction you did?
Bunch.
It's really simple, you just combine hydrochloric acid and sodium hydroxide. And you figured out reactions that way. What type of function is enthalpy? State function. What's the beauty of working with state functions versus path functions? Only the final and the initial matter, right? The other benefit is, which you guys have utilized before, how many steps could you take to really figure out the change in that state function?
As many as you want.
Yeah, as many as you want. That's the beauty of it. You can take as many steps as you want. It doesn't matter because all you care about is the initial and the final. And that's what Hess's law is about. It's about using other little steps to get the overall change or to parse out that step that you care about. So, the heat of a reaction can be determined by the sum of delta H reactions, individual steps of the reaction. So we could look at breaking apart a reaction into simple steps, especially if we know heat's formation. So let's look at an example. Gen Chem knowledge. What's the name of that guy?
Iron trioxide.
Yeah, oxidation state's good. They're going through naming right now. There's a couple of them that have exams and they are like 100% not ready. And 2, they think they're gonna get away with not naming things. Or souls. Okay. wanna figure this out, how would we do it? I'm just asking, like, well, I throw that as a daily problem, how are you gonna figure it out?
Look up the delta H's.
Yeah, look up the delta H's. If you look up the delta H's, don't use Google because a lot of times they're just wrong or they have the wrong conditions or they're not explicit about the conditions. You'll only find this one and this one. You won't find that guy. Actually, I lied. You can't find that guy. And I wanted to do a different type problem, but we'll just keep running with this one. Yeah, you can look those down. So. We can look them up though. And we got A, B, I don't know why I lowercase that one, C. We're gonna split this one into a series of different steps. So we can look at each of these reactants and we can consider products and consider their heats of formation, right? We can break this guy up into its constituent elements and hopefully look in the back of the book and see a delta H of formation. So here we're talking about taking this guy, breaking it apart. What are we gonna break it apart into?
Iron and oxygen.
Yeah. Okay, iron, how's that found in its reference state? Solid, yep, and then you got O2, right, count as what?
Gas.
Gas, okay. Coefficients. What do we got for the iron? 2. Oxygen. One of those uncomfortable ones.
3 over.
Yeah. Okay, and we'll call this delta H not A. What is this? Or what's the reverse of this? I flipped it the other way around. What is it? Yeah, heat of formation. Of iron 3 oxide, right? However, to make this true, what do I gotta do to this? Negative sign, yep. B, let's talk about breaking apart, what's the name of that compound? No, need charges. Yep, sulfur tetroxide. You were right, if it had a negative 2 charge, sulfite all the way. I don't bring him back bad memories from Gen Chem. Let's take that. And look at breaking it apart. If we bust this thing apart, what are we gonna get?
Sulfur and oxygen.
Yep. Sulfur, does anybody know how it's found? What was that? It's found as a solid, yeah. It's S8, like if you have it individually, but if you have it in a network, it forms something a little different. We're just gonna leave it as sulfur solid. And how many of those guys do we need? 3, and then we have O2, right? And how many of those guys do we need? Yeah. Can anyone see what this one is? the heat of formation for that one will be 0, not for this thing though. Let's try to pull out a common factor. What common factor can we pull out from this reaction? Yeah. Pull out 3. Does that help? What is this? What'd you see for the last one?
It's the reverse of the delta H.
Yeah, it's the reverse of the heat of formation of that sulfur trioxide liquid. But what do we have to multiply it by? Yeah, because that stoichiometric coefficient is there. The last one. We want to talk about forming this guy. Okay, we gotta break this thing up into its constituent elements. Tell me its constituent elements.
Iron,
Yep, so 2 irons. What else?
sulfur,
Yep, how many of them? 4, yep, solids, and then we have O2, right? And how many of those do we got? Yep. 4 times 4, 16, 8. Okay, what is this thing? Heat of formation of that iron 3 sulfate. These heats of formation, what's the beauty of those?
You know,
Yeah, you can look them up. Some nerd in the past figured out all these things. We don't have to worry about it. All we have to do is look those values up and sum them. Does anyone want the numerical values for them? No. You work it all out. 4, 4, 4.8. That many kilograms. My phone's telling me to shut up. Is this process endo or exothermic? It's exothermic, so if you were to conduct it, what would you want to be careful about? Would you want to hold this reaction vessel? No, it's giving off a lot of heat. So what this can tell you right away is will it or won't it be dangerous? This is a large amount of heat. Next week, if it's not raining during the week, we'll conduct the thermite reaction and we'll calculate that one, or I'll have you do it for a homework problem, okay? All right. I didn't get to everything I wanted to, so we're actually only gonna have one daily problem. Are there any questions about what we talked about today? Okay. We learned about heats of formation. We refreshed everybody's mind on what Hess's law was. And we showed we could take a reaction where we really didn't know what the delta H was going to be, but we could use those heats of formation to figure out what would the change in enthalpy be. So you should be able to do a problem like that, hint, hint, So know how to utilize that, and also understand what reference states are and so on. Before we leave today though, that delta H, talk about heats of formation. Why are we not just saying H? Why are we always talking in deltas? Anybody have an idea? Because this is all a relative scale. We've set the scales where the heats of formation of the different elements are at 0, and we're just measuring off of that. We can't ever measure H directly, but we can measure changes in H. That's why when you look through, you only see delta H, you won't see H, unless we're talking about like a theoretical idea or a theoretical concept. So these, they're all on a relative scale. We've set a reference and we base everything off of that reference. Does that make sense to people or not really? How many people feel like they get what I'm talking about? Raise your hand. Okay, ish. Okay. It's all because we set a reference and we base it all off of that. It's just like Celsius and temperature. We said, all right, 0 is where water freezes. Is that an absolute scale, the Celsius? No. Delta H's are also not an absolute scale. The problem is because we can't measure an absolute. We can only measure changes. The weird thing is, there's one state function that you can measure, one important state function we'll talk about later, S. You can measure or predict entropy entropy directly. All right, keep that as some of your interest, but I just wanted to talk about that.